We want to continue our discussion with hypothesis testing. And there's a couple of different ways to do hypothesis testing. One of the major differences between the two ways is whether we use a z-score, the cumulative normal score, or the t-score. Now, just like with confidence intervals, we used a z when our population standard deviation, sigma, is known, when we have that information. If our population standard deviation is not known and we have our sample standard deviation, we use our t value. So we're first going to concentrate on when to use the z value when sigma, or the population standard deviation, is known. So the test statistic that we will use to calculate this, we have seen before. Z is equal to our sample mean minus our population mean divided by sigma divided by the square root of n. And you'll notice that I'm putting parentheses around that denominator. Make sure when you do this calculation, if you put it all in your calculator at one time, that is fine. Just make sure that you calculate the numerator, calculate the denominator, and then divide. So putting this in your calculator all at once, just make sure that you include these parentheses, okay? So be careful with that. Okay, so there are two different methods even within this that we can use. The first one is called the critical value method. The critical value is the z-score that forms a boundary between the values that are considered unusual and values that are not. Think about what is considered unusual. Well, where we were talking back in our probability sections, anything with a probability of less than 0.05 was considered unusual. In our cases with hypothesis testing, anything that is less than our alpha or our significance level will be considered unusual. Our critical value will actually be looked up on the z or the t chart. It is not the actual calculated value. There's a difference between the test statistic and the critical value. The critical value corresponds to the alpha, the significance level. And we will look at how to actually calculate those in just a little bit. So we want to look at what we also call the critical region. The critical region is the region which contains those unusual values. So if the test statistic is in the critical region, we reject the null hypothesis. So think about whenever we're here, and let's say that we're looking at a left-tailed test, so it's left-tailed. This area right here is our critical region. The value that goes right here is our critical value. Now, if our test statistic, where we put it on a z-chart, 0 to, for example, if I'm looking at the values, and here's 0 in the center because we're talking about the z's, and we could have negative 2.5 or anything like that over here, positives over here. If my test value falls in here, then we will reject the null hypothesis. If the test value does not fall in there and it falls somewhere in this unshaded region, we will not reject the null hypothesis. And again, we will continue discussing this as we go through. The significance level is that which we want to really pay attention to. This is the value or the probability used to determine whether an event is unusual or not. If we're not given a significance level, then we assume that it is 0.05 because that's what we've been taught is considered unusual. This is denoted by our alpha. So alpha is our significance level. So let's look at the differences between left-tailed, right-tailed, and two-tailed tests. So when we're looking at a left-tailed, which I had drawn right above, and I'm going to draw two of these. Both of these are going to be left-tailed. So my shaded region is going to contain my alpha. This is the critical region. So this also contains your alpha. It is also the critical region. And when we're looking at it, obviously if it's on the left side, it's going to be a negative z based off of our alpha. So it's a negative z based off of our alpha because it's on the left side. Okay? So z alpha, let me put that up here, z sub alpha is going to be our critical value for a left-tailed test. Negative here. Now then, if my test statistic is here, and I'm going to note this z with a t, that is my test statistic that we have calculated. And then I will put one here, z sub t. So if my test statistic falls here in the not shaded region, then you do not reject the null hypothesis. So if it's not in the shaded region, do not reject the null hypothesis. If it is in the shaded region, then we will reject the null hypothesis. And obviously on these, they're probably negatives. They're probably on the same side of there and everything. It's just whatever value that our test statistic is. That is for a left-tailed test. A right-tailed test, not a lot changes here. A right-tailed test, we have our normal distributions, and we're going to shade in the right tail down here. And we have our normal distribution again. And we're going to shade in the right tail down here. Okay, so in here goes our entire alpha, which is also called our critical region. So this is our entire alpha. Our z alpha is our critical value. Now on a right-tailed test, our z is going to, critical value is going to be positive because it's on the right side. Because if you recall, we're talking about z's and 0 is always in the center. Okay? Then we're going to look at our test statistic. If I have zt here, that's my test statistic that I have calculated. If it is here, it is not in the shaded region, so do not reject the null hypothesis. It's not in the shaded region. If my test statistic is here, then it is in the shaded region, and we do reject the null hypothesis. So if you kind of get the sense here, in the shaded region, reject. Not in the shaded region, do not reject. Now, two-tailed tests are slightly different. Well, first of all, they have two tails. So I'm going to draw here, and I'm going to shade in both tails. I'm going to shade in both tails. And this one I'm going to put a little bit lower so that I'm not trying to overlap or anything. And I'm going to shade in both tails and shade in here too. Okay, so my alpha is my significance level. The alpha is what goes in each side. Well, in this case, I have two sides. So what actually happens is we take alpha and we divide it by 2. Alpha and we divide it by 2. Alpha divided by 2 is going to go in here. So our significance level, we're going to divide it by 2 and place in here. Which means whenever we're talking about our critical values, over here it's going to be negative. It's going to be z for the alpha divided by 2. And here it's going to be a positive z for the alpha divided by 2. Now these two values are going to be the exact same absolute value number. They're just going to have opposite signs. Recall back when we were talking about confidence intervals, the same thing happened. We added and we subtracted the same value. We have a negative value and we have a positive value of the same value. But we have to divide that alpha by 2. The same concept happens though. I could have a test statistic here, or I could have a test statistic here, or my test statistic could be here. If it's in any one of these three places, is it in the shaded region? No. So here I do not reject the null hypothesis, because it doesn't matter if it's here, 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 in between, anything like that. If it is not in the shaded regions, we do not reject. Now over here, I could have my test statistic here, or it could be over in here. On either one of these cases, if it's here or if it's here, then I will reject the null hypothesis. So on a two-tailed test, we have to be a little bit careful because we're looking at both sides. We have to pay attention to both sides there. Now I want to look at one table first. It's called Table 9.1. It is the table of critical values for commonly used significance levels. This table only use with Z. Only use if we know population standard deviation. We cannot use it if we do not know the population standard deviation. These are our common critical values. Left, and if you know if it's a left-tailed, you'll use these. If it's a right-tailed, you'll use these. The program has actually already divided our alpha by 2 wherever it looks up the two-tailed. Okay? So be careful on those. Now, I want you to go through and practice finding the critical values on some of these, and then we will look at some other examples. So I just said I wanted you to practice looking up some of these critical values. Well, let's go over to the Z chart and see if we can figure out how to find these. Okay? So I want to look at a couple of examples, such as if alpha is equal to a 0.02 for a left-tailed test. So in this particular case, we're looking up as 0.02. So here's 0.02. We're looking at a left-tailed test. This is our alpha, this is our probability. So what happens is we have to go to the center of the chart and look up 0.02. So whenever I do that, 0.0, here's 0.01, here's 0.02. I'm going through here. Okay, it's between these two. It's actually closer to this one. So my z-score is a negative 2.05. That is my critical value. Okay? When I first start and I use the alpha and I look it up on the chart, that's the critical value. Now, let's look at a different example. Let's look at where alpha is 0.03 for a right-tailed test. Now, on a right-tailed test, we're over here on the right tail, I can still look up 0.03 on my Z chart here. So 0.03. Okay, so this is the one that it's closest to. This is showing a negative 1.88. Well, is this going to be negative over here? No. Remember that my deal is symmetric and I can flip it over. So this is actually going to be a positive 1.88 for my Z critical value. Okay. So we have to be a little bit careful when we're looking these up on the charts. When we look up a two-tailed test, so let's say that alpha is 0.02 for a two-tailed test. Well, on a two-tailed test, it's not going to have the same Z as this left-tailed test did. What we have to do is we have to take 0.02 divided by 2, because this entire thing, entire shaded area, has to add up to 0.02. So I'm actually going to look up a 0.01 on both sides. Okay? So where I look up a 0.01, this is the one that's closest to negative 2.33, and so this would be a positive 2.33. So my critical values would be negative 2.33 and a positive 2.33. That's where the alpha divided by 2 comes in. I have to divide this by 2 for a two-tailed test before I look it up. So now, again, practice some of these and then let me know if you have questions.